Nice to meet you, everyone. I'm Doyeon Hwang from NC University, presenting AdaFed, an adaptive selective aggregation method for heterogeneous federated learning and autonomous driving. This is joint work with Sun Jun Hong. Autonomous driving companies deploy very different architectures, from camera-only planners like VAD or UniAD to multi-sensor fusion systems like transfuser or interfusers. Driving data is expensive to collect and hard to share across organizational boundaries, and federated learning is the natural answer, since models can learn collaboratively without centralizing raw data. But standard federated learning, like FedAverage, assumes every client runs the same model. In reality, parameter counts range from 21.8 to 42.7 million, and backbones differ between ResNet 34 and 50. That assumption breaks, and naively averaging mismatched parameter causes negative transfer, degrading performance rather than improving it. This is our framework. On the left are 7 client models, in the middle is tier-based aggregation, and on the right is AdaFed selective acceptance mechanism. The key idea is we group models by shared architectural components, which we call tiers. So models sharing a ResNet 50 backbone are aggregated on that backbone only. And instead of applying the update blindly, each model evaluates the candidate on a validation set, and it accepts it only when it actually helps. This single decision protects vulnerable models and saves a huge amount of computation. We split the 7 models into 4 tiers. Tier 1 is the ResNet 34 backbone, which includes TCP, transfuser, and lav. Tier 2 is ResNet 50, including interfuser, ResNet, and VAD, and UniAD, which is the largest tier. We also have a BEV encoder tier and a BEV lift tier, and BEV lift tier is only shared by VAD and UniAD. Only tier-matched parameters are aggregated, while each model's task-specific planning head is always updated locally and never shared. Here's the algorithm. Each round, for every tier, we compute aggregated weights and apply them to a model as a candidate. We measure AD on the validation set. If the candidate is better than the current model, then we accept it and run local training. And if it's worse, we reject it, and more importantly, we skip the local training entirely. That guard prevents negative transfer, and skipping rejected models cuts computation dramatically. Our experiments run on CARLA 0.9.16. We trained 23,580 samples, validated 5,895 samples across 15 episodes. The protocol is 2-staged. We first build an imitation learning baseline, which is also called as an IL baseline, then start federated learning from those weights, running 10 rounds with 2 local epochs each. All 6 strategies are evaluated under identical conditions, so the comparison is fair. Our metric throughout is average displacement error, ADE, in meters, so lower is better. This is our heterogeneous federated learning environment, or short, HETEFL environment. All 7 models run simultaneously in CARLA. Let me show you a video of it on YouTube. So these are the imitation learning baselines. ResNet 50 models consistently outperform ResNet 34. Interfuser is best at 1.27 meters, while lav lags at 2.09. There's a subtlety. Lab uses BEV encoder but with ResNet 34 and still underperforms VAD, which uses BEV lift with ResNet 50. So backbone depth is a stronger predictor than BEV encoding alone. Training times range from 34 to 210 minutes, and that gap is exactly our motivation. Can federated learning lift the weaker, cheaper models without paying for expensive architecture? This is our central comparison. The headline results: no conventional federated learning strategy beats the IL baseline. But degradation varies enormously, and that's informative. Fed average is most stable for ResNet 50 models within 0.05 to 0.13 meters. Because the 4 model tier averages well, scaffold is strongest for ResNet 34 through drift correction, but catastrophically fails for VAD over 5 meters. The knowledge distillation methods, FedMD and FedDF, performs much worse. Consensus across heterogeneous architectures produce conflicting gradients rather than useful knowledge. And in green, AdaFed achieves the best performance for VAD and UniAD, the two models that suffer most everywhere else. Let's see why AdaFed works. VAD shares its BV lift tier with only UniAD, making it very vulnerable to blind aggregation. A two model tier has too little consensus to average safely. AdaFed rejects the harmful updates while accepting the beneficial ResNet 50 ones, reaching 2.05 meters, a 0.26 meter improvement over FedProx. Notice the staircase. The model drops when an update is accepted, and like this, and the flat segments are rejected rounds, like this. This gives us interpretability. Each step marks a round where aggregation genuinely improved the features. Efficiency is AdaFed's second strength, and it's dramatic. It completes in 146 minutes, only 22% of Fed average runtime, and 4.5 times speed up. Because rejected models skip both aggregation and local training, AdaFed avoids the dominance cost entirely rather than just trimming it. The full baseline budget is roughly 60 hours, while AdaFed needs just 2.4, less than any single baseline strategy. So you get the best performance on vulnerable models and the lowest cost. To conclude, first, large, well-matched tiers do fine with simple Fed average. Second, scaffold is optimal for ResNet 34 models. Third, KD-based models are unsuitable for heterogeneous driving FL. And fourth, for small vulnerable tiers, AdaFed delivers the best performance at 20% of the cost. The backbone similarity alone isn't enough, and downstream model compatibility matters just as much, which is why VAD struggled everywhere else. So practical deployment should use a tier-aware hybrid strategy, not a single global one. Future work includes combining AdaFed with tier-specific baseline strategies and validating on real-world multi-fleet data. Thank you.